When you hold an ESP32C3 DAV kit in your hand, you're not just holding a board, you're holding a compact IoT computer with built-in Wi-Fi, Bluetooth, memory, and general-purpose pins. Imagine designing a sensor that measures air quality in a factory, streams that data over Wi-Fi, and lets you control fans remotely, all from this single chip. That's the power of understanding its architecture. In this lesson, we'll break down the ESP32C3's core features and peripherals, not as theory, but as tools you'll actually use. You'll see how its CPU, memory, GPIOs, and serial interfaces tie directly to real-world projects, and by the end, you'll know exactly why each feature matters and how to apply it in your builds. The ESP32C3 isn't about flashy specs, it's about balance. It runs on a single-core RISC-V CPU at 160 MHz, plenty for IoT tasks without wasting power. Think of it as a reliable workhorse rather than a race car. With 400 KB of SRAM and external flash, you have enough room for sensor logic, connectivity stacks, and moderate data handling. What makes it shine is the integrated Wi-Fi and Bluetooth 5.0. In one project, I built a warehouse temperature monitoring system where Wi-Fi pushed readings to the cloud, while BLE let workers quickly check values on their phones without internet. The point is, connectivity isn't an add-on, it's built into the chip's DNA. That combination of moderate processing, sufficient memory, and built-in networking is why the ESP32C3 is a favorite in production-grade IoT. If the CPU is the brain, then GPIO pins are the hands and ears of the ESP32C3. They let you sense buttons, drive LEDs, or trigger relays. On the C3 you have 22 GPIOs, plenty for most IoT tasks. But here's the catch, not every pin can do everything, so you'll always need to check the data sheet before wiring. In one home automation project, I connected motion sensors to input pins while using outputs to switch lights and fans. It's not just about toggling high or low. These pins can be multiplexed for UART, I2C, or PWM depending on your needs. Think critically. When you design a board layout, how many pins do you dedicate to sensing versus controlling? That trade-off thinking is what separates hobby circuits from reliable IoT systems. Digital pins are great, but the world isn't just on or off, it's analog. The ESP32C3 includes up to 6 ADC channels with 12-bit resolution, so it can read varying voltages from sensors like light or soil moisture probes. In agriculture projects, I've used these ADC channels to monitor soil health and trigger irrigation when thresholds dropped. Timers are equally powerful. They allow you to schedule precise tasks, from blinking LEDs at exact intervals to measuring pulse widths from ultrasonic sensors. A practical tip: when you need consistent timing, never rely only on software delays. Use hardware timers for accuracy. Ask yourself, in your project, what data comes in gradually, like temperature, and what needs strict timing, like motor control? That's where ADCs and timers fit perfectly. The ESP32C3 becomes truly powerful when it talks to other devices. That's where UART, I2C, and SPI come in. UART is your simplest channel, perfect for debugging or modules like GPS. I2C uses just 2 wires and is brilliant for chaining multiple sensors and displays with minimal pins. SPI is your go-to when you need speed, like driving a TFT display or reading from external flash. Here's a real project story. I once built an IoT energy meter using I2C for a current sensor, SPI for high-speed data logging, and UART for debugging, all on the same chip. The key takeaway is understanding which protocol fits your device's needs. When designing, always ask, do I need low pin count, high speed, or simple serial communication? That choice can make or break your design's reliability. Pulse width modulation, or PWM, is how the ESP32C3 simulates analog output. Instead of a steady voltage, it rapidly switches between high and low, creating an average signal that devices respond to. That's how you dim an LED smoothly or control a motor's speed. In robotics projects, I've used PWM channels to control servo positions precisely. In IoT lighting, PWM allows smart bulbs to adjust brightness or color temperature. One trick I've learned: always check the resolution and frequency settings. Too low a frequency and you'll hear motors buzzing, too high and LEDs may not dim smoothly. When you're mapping out a project, ask yourself, what needs variable control rather than just on and off? That's where PWM is your tool of choice. This table sums up the ESP32 C3's main features in one view. Notice how it's not just about raw specs but about how each maps to real-world design. The single-core CPU isn't a limitation when your project is about sensors and connectivity. The integrated Wi-Fi and BLE remove the need for external modules, which cuts cost and complexity. Multiple serial interfaces give you flexibility when expanding with peripherals. ADCs and PWM make it capable of handling both sensing and actuation. Think of this as your cheat sheet when planning projects. You'll constantly come back to these specs to decide what's possible on this board. Now you've seen the ESP32 C3 not just as a board, but as a system designed for IoT work. You've learned how its CPU and memory set the baseline for performance, how GPIO, ADC, and timers let you sense the environment, and how UART, I2C, and SPI extend it to countless devices. PWM closes the loop by giving you fine control over actuators. These aren't abstract features. They're the exact tools you'll use in smart homes, agriculture, robotics, or industrial IoT. Keep this framework in mind, because every project you design will be a negotiation between these resources and your application's needs. That's the real art of working with microcontrollers.